everyone. I'm Dr. Renee Mehrra, and today I am joined by my guest from Vienna in Austria. He's a scientist whose group just recently was awarded the renowned Austrian Research Award, the Houska Prize of 2021. And this group was awarded for their work on high reliability power electronics. And before that, in 2019, group had got an award in the International Electronic Fair in Munich, Germany for innovation. So thank you very much. It's Dr. Bernhard Czerny from Vienna, Austria. Thank you for joining today.
Thank you for having me.
And Dr. Czerny is the program director for the bachelor's program for applied electronics and photonics at the University of Applied Sciences in Burgenland in Austria. He received his doctorate in physics from the University of Vienna. He's published over 30 scientific papers, 3 patents, and numerous reports in the field of microelectronic reliability. It's such a tough word for me, but I'm going to ask him all about that. And his research group, as I mentioned, won this under the leadership of Professor Dr. Golta Khatibi, the renowned Houska Prize. So congratulations for the award in Munich, in Germany, and for the award in Austria, the highest award that has been given, and for application-driven research in Austria. So thank you very much for joining us. Before we go to your machine that's for testing methods, which is called BAMFIT, I want to know, first of all, about your research and also what are powered electronics.
Okay, thank you very much again for having me and for this opportunity to talk here. My field of research is reliability in power electronics, and power electronics are used all over the world in high power engines and industrial machines, such as wind turbines, power plants, such as electrical vehicles, powertrains, but also in smaller consumer products, such as a washing machine and so on.
Even phones, cell phones as well?
In phones a little bit. So every charger has a power semiconductor device inside. And they are connected via wire bonds to the outer terminal electrical connections. So, and there are hundreds of these electrical interconnects in one of these devices. So, if one of these fails, then the product has a defect and has to be replaced. If it is a phone charger, it's not that of an issue. You can buy it in the next store. If it is a train, then it's much more cost intensive. And also, if this is an offshore power plant, then you have to go maintenance, and this will cost millions of dollars. Or you have, God forbid, catastrophic failure and an accident or something like that. But the thing is that in power electronics, you are very keen to produce very reliable products. Mm-hmm. Because in the powertrains and offshore wind turbine plants, you want the operation over a long period of time. So 5, 10, 15, 20 years. You don't want your electrical car to shut down after 5 years just because one wire failed. Mm-hmm. So that's what we were working on. And we are looking at the reliability of these critical interconnects within the devices that are used in such applications.
I see. So that's called the reliability issues, the testing methods that you have created, the BAMFIT machine, which is right behind you, and you're in the lab right
Yep.
now. So this is the machine that it tests the reliability, and as well as in the developmental stage of the product, and the maintenance and the lifespan of that product. So you're looking at one of the critical parts of the high-powered product and looking for it and seeing that what's going to be the lifespan?
Yeah, so during the lifespan, these products, I have one here, I can show you. This is a power electronic device used in industrial engines and also powertrains. And as you can see, I put it a little bit closer, you have hundreds of small wire bonds inside, and only if one fails, then the whole train will stop. And the issue why they fail is not, or in most cases, not due to outside circumstances, but just due to the operation itself. So the thermal cycles during the operation, the heat and cooling contractions will start a fatigue crack to propagate, and one of these wires will lift off. And this will then go after 5 or 10 years, just under normal operation. And a critical part is to know how long or how reliable your product is. And there are several testing methods to do that, but most of the testing methods are very, very time consuming. A few testing methods last about 10 years as well. So if you have developed a product, you're testing it for 10 years, then you are already in the generations 10 or something like that, what you're selling, and you have not tested it already. Then you have a little bit faster testing methods, but usually this is in the range of a few years. And for a development stage, this is very, very long. And so what we have done here with this device, which we implemented in such a bonding tester, we created a very, very fast fatigue tester. So we substituted this thermal excitations and cycles, which go over 20 years, with just mechanical vibrations, very, very fast mechanical vibrations. So we go with about 60,000 vibrations within a second for only a few nanometers. And this will generate a failure in the wire. So we can test one of these wire bonds within a few seconds and extrapolate and simulate a thermomechanical fatigue, which would be in the range of about 30 years.
So you're using mechanical fatigue in these high-powered electronics, like we're talking of trains and buses, electric vehicles, industrial engines. So tell us how you're using this mechanical fatigue, and what does it actually mean in layman's words?
So this mechanical fatigue is, so we are looking at the critical sites of one of these products, and this is the directly interconnection of the wire to the semiconductor. Mm-hmm. And this is prone to fail after certain years. And what we are doing, we simulate the expansion by mechanical fatigue, by mechanical oscillating the wire against the contact. And this will generate in a few seconds a crack which would propagate through this interface. And usually this will take a year, and that is accelerated. In real life, this will take about 30 years. So what we can do here with this machine, we can oscillate the interconnect and simulate 30 years within a few seconds of testing time. And this gives you a huge advantage and a huge opportunity to test several materials, several types of layers, and you can switch them and do experimental and not only simulations to determine which combination is the best. Otherwise, you have to wait 1 year for one combination, then you test the next, and so on and so on. So you can do this within 1 week, and you have a whole range of materials, thicknesses, design layouts for your product.
I see. So the previous testing methods took a very long time, like you mentioned, many years. And this one, within a few weeks, we can determine and discern how long this product is going to function optimally.
Yes. So this is only looking at a certain fatigue failure of the interconnect, but these failures are the most prominent, and these devices are prone to fail due to this failure, and that is why this failure mechanism and failure mode is such important. And with this method, you can accelerate this and do this in the development stage, and don't lose enough time for your design and development of your materials. And then you can get very, very high reliable products out of that. It doesn't replace the existing testing methods, but it gives you a very, very small margin where you can then put a 2-year testing methods into use of an already optimized design.
And this is for manufacturers all around the world, I believe, like even in the US, this is being used, the machine?
This machine is by Bondtech, and this is distributed all over the world for manufacturers. We were doing our research with our company partner in Finland, but this is for all over the world, and these semiconductors are used everywhere, and increasingly so.
Right. You have that high-powered module that you have, like for bigger high-powered electronics. It's a bigger power module, right?
This is the bigger module. This is in the range of about a few megawatts, which operates in powertrains, and there are also smaller modules, which is something like that, which operates in welders or in dishwashing machines, and medium-sized are then used in electrical vehicles and so on and so forth. So it's different types, but as I said, the critical parts you want to have a high reliability for, of course, products or applications which are last a long time. But all these interconnects are still in use also in your phone charger. But as said, okay, they want you to reinvest in a new phone, but not in a new train.
Now, you spearheaded the research from the wire bonds, right?
Yeah.
So share with us how they work in this in the BAMFIT machine.
So the BAMFIT machine, this is our testing method that we have implemented in this BAMFIT machine. The machine itself is a bonder itself, so you can produce the wire bonds on this such a semiconductor device. Mm-hmm. So you can produce these wire bonds in the machine, and then you can test this with the with our method on the same machine. So you can stitch them. It's more or less, you can imagine this as a sewing machine. So there is a plain chip, and then you sew the wire and the wire connection on top of that. And with our tester, you detach them again, and you measure how long it will take you to detach this. So the time duration within a few milliseconds for the detachment will give you how many cycles this interconnect will hold. Mm-hmm. And these cycles, then, this is in the range of about millions to 100 millions of cycles within a few seconds. and this will give you then about 100 million of cycles in 30 years, the corresponding to mechanical stresses in the field.
I see. So do you train the manufacturer's department for research, who is testing the critical parts of their product? You give them training?
Yeah, we'll also give them training, but we are more in the range of research. So we are more in the range in the field of collaborating with scientific collaboration with these companies.
Right.
But this is more or less in this kind of field. It's more or less the same. So they will learn through a scientific research topic and research project how to use such a new and different testing method as a standard method.
So what has been the reviews so far? I'm sure they've been great because you've gotten the highest award from Austria, the Houska Prize. Are you going to modify it even further? Or?
The response is very well received. It is very difficult because all of these companies have different demands, and it is a very small margin where for the application and for the understanding of all of this. So what we have done and still doing, try to push this highly accelerated mechanical fatigue issue into the mindset of the companies, so that they can use this advantage in their products. It is difficult because the problem is that the standard testing methods are established, and they have in a certain range norms and standards which are applied, and they will tell you how long and how you have to test this. And to implement a completely new and innovative method in such a market is very difficult. But right now we had a huge success with that, and we are trying to push this further. And in the scientific community, it's very well received. And we again, with the Houska Prize, we got a really good response from the scientific community for that part. But again, it's a mindset that a few seconds of testing to replace 30 years of operation is a little bit difficult to understand.
Right, that's true. And your group got $150,000, the Houska Prize. Is
Yep.
that? Yes. Now, would you like to develop something? That's my perception. Something that, which you already have, the bumpet machine, but a machine that you want to invent that not just tests a critical part in a product, but a few critical parts in the product, so that even increases the reliability and the durability of the product. Yeah.
So as most of the scientific processes this is not an overnight invention. This was done over several years, about 10 years of development, and it got from one stage to the next until it reached commercial and a productive stage that it can be applied. And this we definitely want to do for normal and broader interconnects within electronics, and also whole sets of electronics, so that you are more versatile for different kind of interconnects. It's solder interconnects or layers, metallization layers, and all of these interconnects you can try to test on a different way. and we are trying to push this idea and development further to go to more broad type of interconnects, not only in power electronics, but also in microelectronics.
Wow. Well, this is fantastic news. I mean, especially for researchers and scientists and for manufacturers, because it really increases the lifespan of their products. And when we're talking of high-powered electronics, you know, we're talking of buses and trains and even dishwashers and anything that's high-powered, and it enhances the lifespan. This is kudos to you. So thank you very much for being the recipient, your group being the recipient of the Houska Prize for 2021, as well as the Prize for Innovation at the Munich International Electronic Fair that was in 2019. That also got big raving reviews over there as well. So thank you very much, Dr. Bernhard Czerny. Wish you all the very best with your further research. And you'll continue as the program director for the bachelor's program in applied electronics at the University of Applied Sciences in Burgenland in Austria. You will continue with that, or you're going to move on to something else?
I will continue with that, and I'm hoping to push the testing method and the testing equipment, which we have here, more into the sensor and photonics part. So LED display design to get more reliable products also in the field of photonics.
Thank you very much, Dr. Czerny. I'm Dr. Renee Mehrra. Thank you so much for watching.